Greetings. We are going to look at semiconductor theory, majoring electronic materials. We are going to define terms, discuss the energy bands for insulators, conductors, and semiconductors. Explain resistivity charts of insulators, conductors, and semiconductors. Next slide. It's good to know that electronic materials are classified into three. This means that all electronics gadgets that we have, they are made up of materials, namely conductors, insulators, and semiconductors. Now, let's look at conductors. What is a conductor? Okay, but they have very low values of resistivity, and the measure of resistivity is ohms. Or conductors, they allow the passage of electric current, meaning they have plenty of free electrons floating within their basic atomic structure. Wait a minute. Do you remember the Bohr atomic model? Yes, you remember. What are the examples? You have copper, aluminium, silver, or non-metals such as carbon, because these materials have very few electrons in the outer valency shell or ring, resulting in them being easily knocked out of the atom's orbit. Right, next slide. Insulators. They are the exact opposite of conductors, meaning they have very high resistivity, and also the electrons are not easily dislodged, meaning they are not mobile. Examples, and by the way, all mostly cables, we find that they have an insulation. They have an insulation. Examples of insulators are marble, quartz, PVC plastic, and rubber. Insulators play a very important role within electrical and electronic circuits, because without them, electrical circuits would short together and not work. Let's pause. Remember, you're looking at a topic called semiconductor theory. And we said the knowledge of semiconductor theories is important in understanding electronic components such as the diodes, the transistors, and the integrated circuits. So let's look at semiconductors. Semiconductor materials such as silicon, germanium, and gallium arsenide have electrical properties somewhere in the middle between those of a conductor and an insulator. The ability of semiconductors to conduct electricity can be greatly improved by replacing or adding certain donor or acceptor atoms to this crystalline structure, thereby producing more free electrons than holes or vice versa. That is, by adding a small percentage of another element to the base material, either silicon or germanium. Now, we are going to look at two types of semiconductors as far as their states, whether they are pure or impure, and one of the classification is intrinsic semiconductors. What are these? Intrinsic semiconductors, they have no impurities added to them, while extrinsic semiconductors, they have impurities added to them. So the other terms here we are looking at called the donor or acceptor. The word donor means giving, acceptor means receiving. Now, that process or that adding donor or acceptor atoms to semiconductor atoms is called doping. And as a result of doping, we have what we call the N-type or P-type semiconductor material. The most commonly used semiconductor basic material by far is silicon. Now, a question, why silicon and not germanium? There are reasons, and it's good you find out those reasons. Now, let's look at resistivity so that we understand whether these electronic materials which are conductor, semiconductors, and insulator, whether they have the same resistivity. What is resistance? It's one of the measure of electrical quantity. And what is it? Resistance is the opposition to the flow of current. And we have a law called the Ohm's law that relates voltage and current. And it states that the voltage is directly proportional to the current flowing through it, provided that temperature and other physical constants are kept constant. So resistivity, given by this symbol called rho, we have this symbol called rho, is measured in ohms meter, and resistivity is the inverse to conductivity. Now, we are going to investigate some of the factors that affect resistance. Now, we have this equation R is equals to rho L over A, where R is resistance in omega, P is the resistivity of the material in ohmic meter, and length of the conductor, units, meters, and cross-section area of the conductor in square meter. This relation is called resistivity equation, a very, very important equation as far as resistivity is concerned. Okay, let's continue. The material of the conductor, for example, copper and silver, we know that copper and silver, they are good conductors, while rubber and glass are insulator and they have high resistivity and poor conductivity. Remember, I have said that resistivity is the inverse of conductivity. Number 2 is length of the conductor. Resistance is directly proportional to the length of the conductor. Longer wires have more resistance as electrons face more collisions. The cross-sectional area. Resistance is inversely proportional to the area. Thicker wires have lower resistivity as they provide more space for electron flow. Number 4, temperature. Resistance increases with temperature due to increased atomic vibration. In semiconductor, resistor decreases with increasing temperature as more charge carriers become available. Now, increase with temperature due to increased atomic vibration, this is what we call positive coefficient of temperature, PCT, while in semiconductor resistance decreasing with increasing temperature is called negative temperature coefficient or negative coefficient of temperature. Type and numbers of charge carriers. Now, we have holes and electrons conducting current. For example, in a p-type, we have more of holes than electrons conducting current. In an n-type, we have more of electrons than holes conducting current. So, doping in semiconductors affect charge carrier concentration and resistance. Impurity in the material. Higher impurity level increase resistance by scattering electrons. Doping semiconductor use controlled impurity to alter resistance. In some materials, external magnetic field affect resistance, e.g. in Hall effects devices. That's advanced for this level, but you can look at it. Frequency of applied voltage for AC circuits. At high frequency, resistance can increase due to skin effect, where current flows more on the conductor surface. We have a chart showing that resistivity is lower in conductors like silver, gold, and carbon. Semiconductors follows germanium and silicon, while insulators have the highest resistivity, for example, glass and quartz. And we have one now, it shows that we are moving from increase in resistivity to a decrease in resistivity. Remember, negative. A negative shows a lower value, while a positive shows a higher value. A very important chart. All right. Energy band for insulators, conductors, and semiconductors. In solid-state physics, the behavior of electrons in materials is explained using the energy band theory. The key concepts involves the valency band, VB, conduction band, CB, and the band gap. For conductors or metals, the conduction band and valency band overlap, meaning there is no band gap, e.g., that is the energy gap is equal to 0. Electrons move freely, making metals highly conductive. Examples of conductors are copper, silver, and gold. Semiconductors. There is a small gap, e.g., that is energy gap of 1 electron volts, allowing some electrons to jump from the valency band to the conduction band when energy is applied. Conductivity increases with temperature or doping. E.g. for silicon, and it's good you know, silicon has an energy gap of 1.12 electron volts. This is a measure. Electron volts is a measure of the energy gap. Germanium has 0.66 electron volts. Insulators. There is a large band gap, 1 greater than 5 electron volts, preventing electron movements. They do not conduct electricity under normal conditions, e.g. glass, rubber, and diamond. So this is a summary of how you can explain insulators, conductors, and semiconductors using the energy band. Now let's look at the diagrams. Right. For metals, the overlap, we say that you can see that we don't have that energy gap. Why? This one is what we call the valency band, and the conduction band, they overlap. For semiconductor, we have a gap, and that is the gap, but it's very small. And we have said that for semiconductors, for example, germanium is 0.06. For silicon is 1.12 electron volts. Insulator, the valency band, conduction band, you can see it's very big. That is the Fermi level. So we have the band gap. This diagram is good as far as the classification of insulators, conductors, and semiconductors is concerned, which we say they are part of electronic materials. Now, let's look at an additional material, emission from semiconductors. This is just an explanation in order to understand what we call this equation, that is Eg, which is energy, is equals to hv. The h here represents the Planck constant, and the v is the frequency. Now, we have a wave number, that is k, and we have energy in the y-axis. Then we have EV and EC, and EG represent the band gap. Remember what we say, that the band gap is measured in electron volts. We have one curve that looks with its minima at this point, and we have another curve with its maxima at this point. Here we explain, for example, the concave and the convex. So we have also holes and electrons. Why am I introducing this? I want us to see the application of semiconductors as far as optical communication or fiber communication is concerned. So we have two types of gaps. One is called the direct band gap and indirect band gap. This is also a good equation. So K is equals to P over H, where P is the momentum and H is the Planck's constant. If the minimum conduction band energy occurs maximum valency energy, it occurs at same value of K. This is a direct band gap semiconductor. Examples of direct band gap semiconductors is gallium arsenide and indium gallium, arsenide phosphates. Otherwise, the semiconductor is to be said to be an indirect gap semiconductor, e.g. silicon and germanium. And now, in indirect gaps semiconductors, we see that in optical communication or in fiber, we don't use silicon and we don't use germanium. What do we use? We use materials that have properties that of direct band gap semiconductors. And you have said that direct band gap semiconductors is if the minimum conduction energy occurs maximum valence band energy occur at the same value of K. Minimum conduction band and maximum valence band energy from this. Electrons are pumped to the conduction band through pumping as a process. And if you are, we will explore more on fiber, or you look at fiber in a different unit, then this material will be very helpful to you. But for this case, I should stop at this point as far as the application of semiconductors in fiber is concerned. But at least we have known that we have two types of band gap, the direct, for example, in gallium arsenide, and indirect for silicon and germanium. That brings us to the end of our lesson 1 part 2. I acknowledge the electronics tutorials, the online channel, and the Byjas for their diagrams. So thank you very much. Assignment 1, what is the difference between the valency band and the conduction band? Using clear diagram, show the following electronic materials. 1 is conductors, insulator, semiconductors. Number 3, explain 5 factors that affect resistance of a material. So it's me, your Mwalimu Ngige. Kindly subscribe, like, and share to the video to get more related material and videos in future. Thank you very much. And in summary, we are progressing on semiconductor, a very interesting topic. Thank you very much and bye.